Hello everyone, my name is Zhang Likun from Chinese Academy of Sciences. Today I'm going to present my work, Interpreting Disparate Privacy Utility Tradeoff in Adversarial Learning via Attribute Correlation. First, introduction. To crowdsource data with high privacy concerns, a solution is to extract data representations which are expressive enough for the target attribute but indistinguishable in the privacy attribute via adversarial learning. However, the quality of representation is of great uncertainty. The privacy and utility loss are weighted by lambda, which is difficult for users to set at the beginning. Even with the same trade-off parameter, the performance differs in attribute to attribute. Therefore, we assume that the uncertainty comes from the complex interaction between the target and privacy attribute. When they are closely related to each other, it is hard to meet both utility and privacy goals. Next, relative work. To quantify such relationship, we borrow two perspectives from the existing works. The first one is explicit attribute label correlation. The latter one is implicit task affinity. Now I will describe our method. To simplify the problem, we binarize each multi-value attribute to a binary attribute set. The first metric is statistical reliability, which measures the level of co-occurrence distribution bias of two attributes. Besides SR, FR calculates the causal effect one attribute has on the other. Imagine each variable of Z is independent from the others. The classifier G is optimized to give larger weights to the variables which have more effect on the output. Some attributes can be encoded by common variables, which means they share common causes and larger similarity. Now it comes to the experimental results. We implement the adversarial learning for various target and privacy attribute pairs to validate the SR and FR on the following two datasets. Then we define metrics for privacy utility and their trade-off. First, we study FR. Generally, larger FR means more privacy leakage, larger utility drop, and worse trade-off performance. Then we change SR from 0 to 1. When it is smaller than 0.3, lambda has little impact on the utility, but the privacy will be better guaranteed with the increase in lambda. When SR gets larger than 0.4, utility begins to drop, and the privacy loss gets larger. When SR further increases larger than 0.6, it remains a large drop in utility, regardless of the value of lambda. In general, we should pay more attention to SR when FR is smaller than 0.5. When SR is larger than 0.6, setting a larger lambda such as 0.7 is recommended. When SR is smaller than 0.4, the larger lambda, the better privacy. When FR is larger than 0.5, setting lambda to be larger than 0.5 is better to achieve the expected privacy guarantee. Otherwise, we should set lambda smaller than 0.5 to achieve the utility. Finally, conclusions. First, we interpret the privacy utility trade-off from the view of attribute correlation. To measure it, we propose SR and FR metrics. Finally, we draw general guidelines to set the trade-off parameter lambda. That's all. Thank you for listening.